All right, so we are very pleased to have Bjorn Poonen from MIT, who will deliver the next Turkish Mathematical Society Distinguished Colloquium. So Professor Poonen got his degree from Berkeley in '94 under Ken Ribbett. After positions at Princeton and MSRI, he was a professor at UC Berkeley until 2008. And then afterwards, he became a professor at MIT. He has numerous prizes and honors, too many for me to list here, but let me mention that he is a fellow of the American Mathematical Society, a fellow of the American Academy of Arts and Sciences. He has held the Sloan Fellowship, the Packard Fellowship, in addition to many awards and honors. And he was one of the few four-time winners of the Putnam competition. So today he will talk about undecidability and number theory. Thank you very much, Bjorn.
All right, thank you for the nice introduction. So let me start with a question for all of you. So can you find three integers whose cubes add up to 35? So yes, I mean, if you think about it for a little while, you'll find the solution here. I mean, here's a nice solution. So 3, 2, 0. Yeah, I mean, and you can ask, and here's another one of this type. So can you find three cubes that add up to 42? And the answer to this one is also known, although this was discovered rather recently, because this is the solution that's known. And so this, yeah, so I mean, yes. So anyway, I just wanted to, yeah, so let me give you, because let's change the number again. Let's change 42 to 114. Anybody? Well, this one turned out nobody knows whether there is a solution to this yet. So and the reason I'm giving you these equations is just to give a sense that it's, I mean, the answer to these questions is not obvious. I mean, because X, Y, and Z could be, I mean, they could be negative or positive. So there's no bound in how, a priori bound in how large they need to be. And yeah, and of course, there are many other questions of this type. And so, well, you can also look at, higher degree equations or equations with cross terms and okay, all right, et cetera, et cetera, et cetera. And so Hilbert asked, and in 1900, well, in the list of problems, that whether there was a single method that could answer all such questions. So so more precisely, he wanted an algorithm that would solve the following problem, where the input is a multivariable polynomial with integer coefficients, and then the output is supposed to yes or no, and not only should the output be yes or no, it should give the right answer, meaning it should tell you whether it should be yes if there do exist integer solutions to the equation given by F. And as I'm sure that Hilbert knew, I mean, he could have asked for a more general algorithm for a more general problem, namely not just for a single polynomial equation, but a system of polynomial equations to be solved simultaneously. But but I'm sure Hilbert knew that that was equivalent to having one polynomial because of this trick. Well, if you want these m polynomials to be simultaneously zero, that's the same as saying that the sum of the squares of those integers, that there's an integer solution to this. So okay, so yeah, but one thing about that Hilbert did not know is what an algorithm was. I mean, because at that time in 1900 there was no formal notion of algorithm, and I mean, well, maybe it doesn't matter so much if you're going to give. I mean, if you're going to give an algorithm to this, I mean, usually if you write down an algorithm, everybody will look at it and say, yeah, okay, that's an algorithm. But if you want to prove that there's no algorithm, then you kind of need a precise notion of what counts as an algorithm. And so this came later, only with the work of Church and Turing in the 1930s. And so the modern interpretation of Hilbert's problem is that it asks to find a Turing machine that solves the following problem. So you input the polynomial, maybe you input the tech code and so just so you have some finite bit string that represents the input, and then the output is just a single bit, yes or no, and she gives the right answer. And the way Hilbert stated the problem, I mean, it wasn't like, is there an algorithm? Is there an algorithm that does this? The problem was, find an algorithm that does this, because at that time there wasn't any problem that was known to be unsolvable. In fact, I think the general the spirit of the times was that everybody, they thought, oh, we will eventually solve all these problems. We're just not yet smart enough yet. But later on, eventually it was discovered that there is no, well, you probably know this anyway from the title of my talk, but yeah, there's no such algorithm for solving this problem. And so what I want to explain is, I want to explain some of the ideas that went into the proof of this theorem. How do you prove that how do you prove that something like this, there cannot be an algorithm? And yeah, and it is done by combining work of a lot of people, like Martin Davis, Hilary Putnam, and Julia Robinson. And then the final step was done by Yuri Matiyasevich in 1970. And so, yeah, in order to explain what these four people did, I'll need to introduce a couple of definitions, because they actually proved something even stronger than this negative answer. And so let me start by giving this definition. So, okay, so before I give the definition, let's talk about a family of polynomial equations instead of a single polynomial equation. So here I'm looking at, okay, so here's an example of a family where I have a polynomial, but I change the right-hand side. And I ask for each of these equations, I ask, is there a solution in integers? And well, obviously the first two equations have no solutions in integers, because they have even no real solutions. But I mean, you've probably heard of a theorem called the four squares theorem in number theory that says that any non-negative integer is a sum of four squares. And yeah, and there's also, well, I guess the upper part of this diagram is the converse to the four squares theorem that says that if an integer is a sum of four squares, then it's non-negative. That's an easier theorem. Yeah. So okay. So yeah. So using in this family, this lets you characterize the non-negative integers as the set of parameter values of the set of right-hand sides for which this polynomial has a solution in integers. So it's this. So this sort of family of polynomial equations sort of cuts out the non-negative integers as a subset of the integers. And so this is what I want to generalize now. Yeah, and to generalize it, let me move this term to the other side. So now I want to think of this as a polynomial in well, 5 variables here, where one of the variables is playing the role of the parameter. Okay, so the general notion is the notion of a Diophantine set. And so for this, you have a polynomial equation in m+1 variables, and this t variable is going to represent the parameter. And what you do with this polynomial is you plug in one at a time, you plug in each possible integer for that variable, and then you try to solve the equation in the remaining variables to find integer solutions to that. And well, and whether or not there's a solution in the other variables will depend on what a is. And so for some a's, the good values of a for which there is a solution, you put those all in a set, call it a. And any set that arises that way is called a Diophantine set. So the example I had on the previous slide with this 5 variable polynomial, and with the a here playing the role of the parameter, this polynomial gives rise to, it shows that the set of non-negative integers n is Diophantine. Okay, so this is one notion that we need. The other notion, besides being a Diophantine set, the other notion is the notion of a listable set. And this has various names in the literature. It's also called CE sometimes for computably enumerable. And in the old days, it was called recursively, RE for recursively enumerable. But I don't know. I think maybe the logicians just decided it sounded cooler to talk about computably enumerable instead of recursively enumerable. Anyway, this is the, yeah. Anyway, so what is this notion? So it's again an adjective that you apply to subsets of integers, and so the set is listable if you can write if there's a Turing machine. In other words, if there's some computer program such that such that if you let it run forever and you look at what the program prints out, then it's exactly the integers that belong to A. So, I mean, one example, it would be the set of prime numbers, for example, because if you know how to program at all, you probably know how to write a program that will print out all the prime numbers if you let it run forever. Yeah, but I mean, they're more complicated listable sets. In fact, going back to those problems I was showing in the first few slides, the set of integers that are expressible as sum of 3 cubes, that's also listable. And so the way you see that it's listable is you run this program. You loop over all x, y, z in a box where x, y, and z are integers ranging from -10 to 10. And so there will finally many of those, and you can, and then for each of those lattice points in that box, you print out the value of x cubed plus y cubed plus z cubed. And then you repeat for a larger box of size, up -100 to 100. And then you keep going like that. And so eventually, if an integer is a sum of 3 cubes, it will be printed out by this program. Yeah, so that's all it prints out. So this proves that this set of integers, the set of sums of 3 cubes, that is listable. But what this does not say is that if you hand me a particular integer and you ask me, is it a sum of 3 cubes? That is not necessarily easy to do, as we saw in the first few slides. So just because a set is listable does not mean that you have a membership test where you can necessarily decide in a finite amount of time whether a given integer belongs to the set. I mean, you could always try running the program and see if it prints out your target integer, but if it doesn't show up for a while, you're never quite sure whether it's going to show up later. Yeah, so at least a priori, it's not clear that listable sets have a membership test. Yeah, in fact, so what I'm going to show you now is it's going to turn out there's some listable sets that are so complicated that there provably is no membership test. So, and this is related to the halting problem of computer science, which I'm sure a lot of you have heard of this. So what this is, but let me just remind you what this was about. So this was about finding, well, so the halting problem is this: you want to have a debugger that will take as input a program and a natural number, and it will predict. And when you have a program, you can only, when you run it, sometimes if you're not very careful, sometimes your programs will end up in an infinite loop, and that's usually not what you want your programs to do, because you usually want them to finish. And so, wouldn't it be nice if there were like a meta program that you could feed in your program into there, and the meta program would tell you whether you'd made a mistake, whether your program is going to enter an infinite loop. And so that's what I mean by a debugger, that it's something that should take a program, and my programs are going to be programs that take a natural number as input, and then the debugger tells you in a finite amount of time, without actually running your program, it will tell you whether it will eventually halt or not. So yeah, okay, so that's the specification of what a debugger is supposed to do, but Turing proved that there is no such debugger. You cannot write a computer sort of a meta program that will do this. And so so you say the halting problem is unsolvable, and the proof is actually not too complicated. At least the idea of it is I can fit in this half slide. So the key idea is to enumerate all the programs. I mean, programs are things that have finite lengths, so you could just string together their ASCII symbols of the characters and then make some big integer that encodes your program. And that way you can enumerate all programs, number them all. So and then if you had a debugger, what you could do with the debugger is you can make this other program called H that does the following. So what this program H does is it takes when you feed it an input integer, a negative natural number x, what H does is it tries to figure out whether program number x, what it's going to do on input x. And it calls the debugger. It asks the debugger, what would happen if, I'm not going to run this program on input x, but I'm going to ask the debugger, what would happen if I did that? Would it halt or not? And then whatever the debugger says that this is going to do, H decides it'll do the opposite. So if the debugger says that X on input X will halt, then H will artificially enter an infinite loop. And if the debugger says it would not halt, then H just decides to halt right then. So that's what you could do if you had this debugger. You could make this other program H. But now if H does this, then you get a contradiction by plugging in, by running H on its own program number. So if you take X to be this number, the number of the program H, then it says that H on input H halts if and only if H on input H does not halt. And so that's the contradiction that Turing found that proves that, well, this program H can't exist, and so the debugger can't exist either. Okay, now what does this have to do with listable sets and so on? So, once you have this one unsolvable problem, the idea is all the other things you can now relate, you can prove that other problems are unsolvable by showing that they're at least as hard as the halting problem. So for example, you can use it to prove that there is some listable set, so that's so complicated that there's no membership test. There's no algorithm to decide, given an integer, whether it belongs to the set L. And the proof is, once you have this unsolvability of the halting problem, you can just encode that into a listable set in the following way. You just make, you take all the numbers of the form 2 to the p, 3 to the x, where program number p halts on input number x. So that's going to be some set of positive integers. And well, okay, so why is it listable? So, okay, it's a little bit, to see that this is listable, what you need to do is you run all the possible programs. There are countably many programs and countably many inputs. You run all of them in parallel, and then each time one of those processes halts, then you print the value of the 2 to the p, 3 to the x. Okay, so you might ask, okay, how do you do this? How do you run countably many programs in parallel? Usually when you have a parallel computer, it only has a finite number of processors. But there's a way to simulate a computer with countably many processors. Namely, even if you just have one computer processor, you just have your computer spend half of its time on the first program, a quarter of its time on the second program, an eighth of its time on the third program, and so on. And so in that way you can you're sort of running all the programs at once, except, well, some of the programs are running very slowly, but it's okay. In theory, if one of them halts, then you'll see it, and then you can print out this number. Okay, so that's why it's listable. On the other hand, there cannot be a membership test for this set, because if there were a way to decide whether a given integer belonged to the set, well, then you could use it to decide whether any program on an input halt. You want to know whether a program P halts on input X, you just ask the membership algorithm whether 2 to the p, 3 to the x belongs to that set. So, but because the halting problem is unsolvable, then this membership test cannot exist either. So okay, so this gives you a source of this. So okay, so that's just to summarize. This gives this listable set for which there's no algorithm to test the membership. Okay, now for the crucial thing that Davis much. Okay, so everything I was saying so far was known back in the. So all this stuff, this was known back in the 1930s. Essentially, as soon as Turing proved it, Turing understood this already. But what Davis, Putnam, Robinson, Matiyasevich eventually proved is this amazing theorem that the Diophantine sets, those are the ones for which the parameter values for which the polynomial has an integer solution. So those are the things that come from number theory, that those sets are exactly the same as the listable sets. And just to give an idea of, it's not hard to see that Diophantine sets are listable in the same way that the sums of 3 cubes are a listable set. But the really surprising thing is the other way. So for example, I said that the set of prime numbers is a listable set. And so this theorem will then tell you that there is some one parameter family of polynomial equations depending on a parameter, such that that polynomial equation is solvable if and only if the parameter value is a prime number. So yeah, just a single polynomial in m+1 variables, and yeah, and it's sort of, and its solvability depends on whether the parameter value is a prime or not. And the proof is also kind of amazing. This theorem, I mean, because the listable sets, those are defined by an arbitrary computer program and what it prints out. And so and this Diophantine set, notion of Diophantine, that's all about number theory. And so in order to prove this theorem, they have to actually simulate the behavior of a universal Turing machine. They have to simulate an arbitrary computer by a series of number theory lemmas. And so they're sort of building up a universal Turing machine. And except instead of like having a big program where you have a big routine that calls smaller subroutines and in a computer program, that it's like you have a big theorem that calls little number theory lemmas, and they call littler number theory lemmas, and sort of a whole series building up all kinds of things like that. Okay, so I'm not going to explain all the details of this theorem. It's all elementary, but it's a little bit involved, and it'll take more time than I have time for. But once you have this, then this already gives a negative answer to Hilbert's 10th problem, because as I explained on the previous slide, the unsolvability of halting problem gives you a listable set for which it's impossible to test membership. And then you just use that same set. That same set will be by this theorem will also be a Diophantine set. And so now you have a Diophantine set for which no algorithm can test membership. And now what does that mean? So that means you have a one parameter family of polynomial equations, depending on a one integer parameter, and you cannot figure out which values of the parameter, the equation is solvable in integers. And so that means you can't even figure out in this one parameter family of polynomial equations which ones of them have integer solutions. So if you can't even do it for that one parameter family, then there's no way you're going to have a single algorithm that works for all polynomial equations in integers. So yeah, so that's the negative answer to Hilbert's 10th problem. In fact, this proves the negative answer in a sort of very strong form, because this Diophantine set, it's described by a polynomial of it's a single polynomial equation in m+1 variables, a fixed number of variables and a fixed degree. So that means even if you restrict Hilbert's 10th problem to just asking for an algorithm for polynomials of a fixed degree and a fixed number of variables, if the number of variables and the degree are sufficiently large, then already just within that sort of bounded family, already there's no algorithm for that. So, all right. So so that's Hilbert's 10th problem. But the next thing I want to explain is that this theorem, it has applications beyond than just giving the negative answer to Hilbert's 10th problem. So let me explain some of these consequences. So one has to do with things called prime producing polynomials, and the other has something to do with the Riemann hypothesis. But what I'm going to tell you is a lot less deep than it sounds. So it doesn't let you prove the Riemann hypothesis or anything like that. But anyway, we'll see in a second. Okay, let me start with the prime producing polynomials. Okay, well here's a 26 variable polynomial. The variables are named A, B, C, D, E, F, G, up to Z. And the claim, what I want to claim about this polynomial is that if you plug in all possible 26 tuples of non-negative integers, and you look at all the outputs of this polynomial, all the integers that are output by this polynomial, and then you throw away the negative outputs, you throw away 0 as well. So you keep only the positive integers that are that are output by this polynomial, then that set of outputs, the positive outputs, are exactly the set of prime numbers. Okay, so now maybe you're surprised that a single polynomial, a polynomial can do that. And well, I mean, I don't expect you to be able to see just from looking at this polynomial why it's doing that, but maybe you can see something, because maybe you notice that, well, it has this, there's this k plus 2, and then it's k plus 2 times something. And if you look carefully, you'll see that where this thing ends is way down here. And so this polynomial actually factors. You might wonder, okay, how that's going to make it kind of hard for this thing to output prime numbers. Yeah, in fact, and also k is non-negative. K is non-negative integer, so this factor is bigger. It's bigger than 1. So maybe it seems like, oh, how could this ever be a prime number? Well, I mean, the only way it can be prime is if the other factor is 1. And then if you look at what this other factor is, it's 1 minus something in parentheses, and the thing in parentheses is a sum of squares. And so most of the time, so it's actually really hard for this even to be positive. The only way it can be positive is if all those squares are 0. And then there's some hard work to show that somehow if all of those squares are 0, somehow that forces k plus 2 to be prime. So I guess that's the mysterious part that I'm not going to try to explain. But yeah, okay. But you can believe that it's possible. I mean, at least I could be telling the truth, because there actually is a k at least in those equations. So, all right. Yeah, and by the way, this is not even the minimal example. There are actually examples that go down to, I think it gets down. I think there's an example with, you can do this with, I forgot what it's, maybe 11 variables. I think maybe that's the record, but if you try to reduce the number of variables, sometimes the degree of the polynomial gets bigger or something. So this is kind of the sweet spot where I can, the number of variables and degree, so that I can actually fit it on one slide. So yeah. All right. So that's it for prime proof. By the way, anybody, you should feel free to interrupt and ask questions if you want, but otherwise I'll just keep going. Okay, so let me move on then to the Riemann hypothesis. So well, okay, so let me remind people what the Riemann hypothesis is about. So there's a complex analytic function called the Riemann zeta function that, at least for, well, first you can define it for, say, for real numbers. You can write down this series, and you probably all know that this series will converge as long as this real number s is greater than 1. But and you probably also know what happens if you try to plug in s equals 1 itself, then you get a divergent series, and that manifests itself by it. Well, it also related to that is the fact that if s approaches 1 from the right, it converges over here, but its values, the value of the sum will tend to plus infinity, so the graph looks something like this. Can you see my little hand? Well, anyway, the graph looks something like that, and so it's tending to infinity, and so there's no way you can extend this analytically to a function on the other real numbers, because it has this, it's tending to infinity there. But if you work in the complex numbers, you can go around that singularity. You can actually, by the process of analytic continuation, you can define this. In fact, you can define it for, yeah, you can define it at all complex numbers except for 1, it turns out. And in doing so, you get values like zeta minus 1, which turns out to be minus the 12th. And well, some people like to pretend that, oh, that means that if you plug in s equal minus 1 into this thing, you get minus the 12th, which would mean that 1 plus 2 plus 3 plus ... equals minus the 12th. Well, of course, that's kind of nonsense, but well, I mean, yeah, I mean, it diverges, but I mean, well, if this thing did converge, then it would be minus the 12th, but it's some sense. But anyway, so yeah, so this is defined by analytic. I mean, the point is you're not supposed to apply this. You're not supposed to use this definition when it doesn't converge. But yeah, okay. Anyway, so this is the function, and it starts out being defined. Actually, it's defined not just for real numbers greater than 1, but any complex number whose real part is greater than 1, because then it's still absolutely convergent. And then to define elsewhere, use this analytic continuation, and it's defined everywhere except for this pole where it tends to infinity at 1. And it's known that this function has zeros. The value of this function is 0 whenever you plug in a negative even integer. And then the conjecture, all the other zeros that are known, lie on this vertical line where the real part of S is 1/2. And the Riemann hypothesis predicts that all the zeros of this function, other than these negative even integers, are along that vertical line. So that's the, okay, this is just a copy of that picture I had in the previous slide. So yeah, so this is the Riemann hypothesis, which is still unproved. And I guess you get $1 million if you prove or disprove it. Yeah, so that all the other zeros besides the negative even integers are on that vertical line. Okay, now what does this have to do with this Davis, Putnam, Robinson, Matiyasevich theorem about Diophantine sets being the same as listable sets? So the point is, yeah, okay. So what it does, it'll give you an explicit polynomial equation, such that that polynomial equation has a solution in integers if and only if the Riemann hypothesis is false. So if and only if there's a counterexample to this. And how do I know this? How do you know? Why does the theorem give you that? How do you find this explicit polynomial equation? So you start by having a computer program. So the first thing you need to know is that there's a computer program that if you let it run forever, it can search for counterexamples to the Riemann hypothesis. So, I mean, yeah, it's not, I mean, it takes a little work to see that there is a way to search, to do a computer search for counterexamples. I mean, one way to do it would be to do various contour integrals around rectangles in the plane, and you can do counter integrals that'll count the number of zeros inside each rectangle. And so you can do that for every, you can do that for lots of rectangles that are not containing any points on the line. And you could ask, okay, see if I can find a counterexample inside this rectangle, or see if there's a counterexample inside this rectangle. And if you do this for all rectangles with rational coordinates, then that if there is a counterexample, you'll eventually find it that way, because you can actually do the contour integral, integrate, 1/2 pi I times zeta prime of S over zeta of S. That's the integral you do to count zeros. And so, yeah, and you can do this numerically. And how do you do this? I mean, there are countably many rectangles, but you can do all these countably many contour integrals in parallel, because as I was saying before, if you have one computer, you can simulate, you can have it run countably many processes at once, each searching for counterexample in a different rectangle. Okay, so that's one way you can do it. I mean, there are other ways you can show that that the problem of finding counterexamples of Riemann hypothesis is something you can do with a search. Yeah, but once you have that, then you have this computer program that will halt if and only if it finds a counterexample to the Riemann hypothesis. And then you use the DPRM theorem to simulate that computer program with a Diophantine equation that has the same behavior. Namely, the Diophantine equation has a solution, has an integer solution, if and only if that computer program finds a counterexample to the Riemann hypothesis. Yeah, and the DPRM theorem is completely constructive. So you can actually, given a computer program, you can actually find the corresponding Diophantine equation. I mean, I'm not sure if anybody's actually written down the equation for this one, but I mean, it will have a bound. I mean, we can say how many we know it has a bounded number of variables, a bounded number of bounded degree. And yeah, so once you have that equation, then all you have to, if you want to disprove the Riemann hypothesis, all you have to do is find an integer solution to that equation, single equation. And who knows, maybe you're lucky. Maybe the equation has no solutions mod 7. I don't think it actually works like that. I think the kind of equations that this process produces are equations that will have solutions modulo any given integers, because it's not going to be that. I don't think that this is a good way to try to prove or disprove the Riemann hypothesis. I think, but I'm just saying in principle. I mean, it's just showing you that sort of Diophantine equations are about as hard as anything else you can do in mathematics that can be solved by that involves like an infinite search. That's sort of the point. Yeah, this really didn't have much to do with the Riemann hypothesis, except for the fact that there is this infinite search that you can do to search for counterexamples. Okay, so all this I've been talking about has been known since 1970, and so what have people been doing in this area since then? So one thing that people have been doing is try to generalize the Hilbert's 10th problem. So instead of just looking at Hilbert's 10th problem over the integers, you can look at it over other rings. So one class of rings you could look at are the classes of rings of integers in a number field. So these are things, yeah. So given a number field, which means a finite field extension of Q, such as the field of numbers of the form a plus b times square root of minus 1. Inside each of those rings, you have an analog of the integers, namely, and those are the numbers in here that are the roots of some integer, of some polynomial with leading coefficient 1, with integer coefficients. And so if you take this set for this field, for this degree 2 extension of Q, you get the ring of Gaussian integers, the numbers of the form a plus bi, where a and b are integers. And there's a ring like this for every finite extension of Q. And so you might conjecture that, well, these rings behave a lot like just the ring Z, the ring of integers. And so you might guess that the answer to the Hilbert's 10th problem over such a ring is the same. So in other words, what's this problem? This means the input, you're looking for an algorithm that takes as input a polynomial with coefficients in that ring and decides whether the polynomial equation has a solution in that with entries in that ring, with coordinates in that ring. Yeah, so okay, so that's the conjecture. Well, I mean, the first thing you might think of, okay, maybe you just go through the proof for Z and just do, just a little couple of tweaks, and maybe the same proof works to prove the negative answer for this other ring. But that doesn't work because there's some things that are special about Z that are used that are not true for this more general ring. And one ingredient in the proof that I didn't talk about is that it uses facts about the Pell equation. So the Pell equation is an equation like this: x squared minus dy squared equals 1, where d is some particular integer. It could be like some positive integer, like there's not a square, so it's something like 5, for example. And then the question is, what do the integer solutions to x squared minus 5y squared equal 1 look like? And the theorem is that under these hypotheses, there are infinitely many solutions, and there's also a way to make a group out of those solutions. And in fact, it's a finely generated abelian group, and in fact, it's a rank 1 group. So that's what happens over Z. But for most number fields, if you try to do the same thing, where you ask about equations like this, and more generally, yeah, you can. The more general notion is the notion of an algebraic torus, and you ask for points on that have, in other words, solutions to the equation that have where the variables take values in OK. Then again, it's a finely generated abelian group, but sometimes you cannot find any such equation where the group has rank 1. And it was essential for the proof that Davis, Putnam, Robinson, Matiyasevich gave that the rank be exactly 1. And so, yeah, so that doesn't work. So the proof that works over Z does not work for this other ring. On the other hand, there are other algebraic groups that you could try in algebraic geometry. There are other varieties that have a group structure besides just things like this. So for example, there are elliptic curves, and so a bunch of people have proved that if you know enough about elliptic curves, then if you know some standard facts, some standard conjectures about elliptic curves, then they will give a negative answer. And so, well, okay, I'm not going to explain what all this stuff is, but anyway, there's some standard conjecture about elliptic curves that lets you construct elliptic curves whose ranks behave in a certain way. And if you know that, then yeah, so Maser-Rubin proved this, and then well, actually the order was kind of back and forth, but anyway, so and Alexander Schlappentock proved that then you would get a negative answer for every ring of integers of every number field. Okay, but this seems, I mean, people have been studying this conjecture for maybe more than 60 years. So I mean, there's been progress, but it's still not quite proved yet. So we're kind of stuck here. So on this problem. So okay, if we were stuck, well, let's just change the problem. So instead of looking at these rings of integers, here's maybe even more interesting question. Suppose you ask about solving polynomial equations where you want rational number solutions. And so you could ask, is there an algorithm to decide whether a multivariable polynomial has a solution in rational numbers. And this one's not yet known. It's not yet known whether it's undecidable or not. So yeah, I mean, one thing you might try is to do some kind of reduction where you use the unsolvability, the negative answer for Z, and somehow use that to get the negative answer for Q, for rational numbers. But I mean, there's an obvious reduction using the fact that rational numbers are ratios of integers, but that reduction goes in the wrong direction, it turns out. So if you just try to simulate, yeah, I mean, that lets you simulate rational equations with integer equations, but that sort of embeds the Hilbert's 10th problem over Q as a subproblem of the Hilbert's 10th problem over Z. And that subproblem might be easier than the full Hilbert's 10th problem over Z. So so the negative answer for Hilbert's 10th problem over Z doesn't necessarily give you a negative answer for this subproblem, the Hilbert's 10th problem over Q. Yeah, so that the naive reduction goes the wrong direction, but Mazur made this conjecture that would, well, I mean, one thing that would give you a reduction the correct direction is if you could prove that the integers could be cut out inside the rational numbers, if they could be characterized, if they formed a Diophantine set. I mean, this Diophantine over Q, meaning that, I mean, I haven't defined this, but it's the same notion as before, where now you have a polynomial that has one rational number parameter, and you ask for which rational numbers is it solvable. And if you can find a polynomial, a family like that, where it's solvable if and only if that parameter is integer, then yeah, if you can characterize integers in that way, then you can do this reduction. So yeah, but okay, so that's what some people have hoped for. On the other hand, Mazur, in order to spite those people, in order to get on the nerves of those people who are trying to prove that Z is Diophantine over Q, made his conjecture that would imply that Z is not Diophantine over Q. So his conjecture, it's a conjecture about the topology of rational points. Namely, you start with a polynomial equation, and you can think about its solution set over the real numbers. So it'll be some sort of, well, not necessarily a manifold, but it might have some singularities, but it'll be, you know, some equation, some hypersurface in R to the n. And then he conjectured that if you take the rational solutions, which is some countable subset of that hypersurface, and you take the topological closure in the Euclidean topology, he conjectured that closure has at most finitely many connected components. So in particular, for example, he's conjecturing that if you look at the rational solutions, they never form, for example, an infinite discrete set marching off to infinity. That the rational solutions to an equation like that never look like that. Yeah, but people have been stuck on this conjecture. I guess, it's 30 years old now. So it's still, yeah, so it's still unknown. In fact, the only case that's known is the case of a two variable when n equals 2. Well, okay, and I guess n equals 1 is okay too. But n, it's known up to polynomials in two variables. So if you have a curve, then it's known that the rational points satisfy this. But even that is a very hard theorem. It relies on Falting's theorem, for which Gerrit Faltings received the Fields Medal in the 80s. So yeah, so it's kind of so yeah. I mean, it's kind of embarrassing how little number theorists know about. I mean, seems like a pretty basic question, but I mean, yeah, we don't even know about rational points and surfaces. What's going on? So okay, so yeah, so I'm going to change the problem again because I was stuck again. So this time I'm going to change. I'm not going to change the ring. Instead, I'm going to change instead of looking at solutions to equations, I'm going to generalize the kind of statements I'm going to make. Instead of looking at sentences like this, where I'm asking, do there exist integers that satisfy this polynomial equation? You could make a harder problem by asking about arbitrary first order sentences. So these are from first order logic. These are expressions that look like this, where you could have polynomial equations using plus and times, and you can have Boolean combinations of those, where you have or and not this. And then you're allowed to use quantifiers, not just existential quantifiers, but also universal quantifiers. So, does there exist an integer x such that for all integers y, there exists a z, et cetera, such that this holds. And if it's a sentence, if all the variables are bound, so then this thing actually has a truth value. It's either true or false when you interpret the variables as running over integers. And the question you can ask, which is a harder problem than Hilbert's 10th problem, is can you decide, is there an algorithm that will decide, it'll take as input one of these first order sentences and output yes or no according to whether it's true or not. And you might say, well, that's a stupid thing to ask because that's obviously a harder, it's a harder problem than Hilbert's 10th problem. And we already know that Hilbert's 10th problem is undecidable. So of course that's going to be undecidable. And in fact, that the undecidability of this was even known before the undecidability of Hilbert's 10th problem. In fact, this was known to Turing already. But the point here is that now that I have this way to make this problem harder, maybe for rational numbers where I don't yet know whether Hilbert's 10th problem is undecidable, maybe if I make the problem hard enough, I can at least prove that that's undecidable. And so this is what Julia Robinson did back in the 1940s. And what she did is she found a way to prove the analog of proving that Z is Diophantine in Q. So she found a way. She found a first order formula with a parameter T, such that the truth of this, if you let T be range over rational numbers, and you ask when is this statement true, she found a statement like this that will be true if and only if that parameter T is an integer. And so she found a way to characterize in a first order way the integers inside the rational numbers. And so that way she was able to do this reduction between Q and Z. And so as a corollary of this, she was able to prove that there's no algorithm to solve the harder problem of deciding truth of first order sentences over Q. And since then, various people, so I and Joachim Königsmann, we've simplified the equation that Julia Robinson did, and we've got it down to only 2 universal quantifiers. We really wish we could get rid of those 2, because if you could get rid of those 2, then you'd have a Diophantine definition of Z and Q, and that would give the negative answer to Hilbert's 10th problem over Q. And actually, Königsmann was able to get rid of one of those. So it's very close. So there's just one universal quantifier that left to answer the question of Hilbert's 10th problem over Q, but that's not known. Oh, and another really frustrating thing is that I said that if Z is Diophantine over Q, then you could do this reduction and prove Hilbert's 10th problem over Q. That's not known, but Königsmann managed to prove that the complement of Z is Diophantine over Q, which, it sounds sort of close, but unfortunately it doesn't seem to be useful for anything. So we're still stuck on the problem of whether Hilbert's 10th problem over Q is undecidable. Okay, and this result, Königsmann, that's been generalized by one of my former students, Jennifer Park. All right, so we're stuck on Hilbert's 10th problem over Q as well, and a lot of people have tried to solve this. Julia Robinson was of course interested in this, and Matiyasevich. A lot of people have thought about it and still not clear what to do. So let's change the problem again. So let me say, so there are a lot of other questions I could ask, right? Hilbert's 10th problem over Z is undecidable. Hilbert's 10th problem over Q, we don't know, but there are lots of rings in between. For example, you could take the ring of numbers of this form. So rational numbers whose denominator is a power of 2. Or you could look at rational numbers whose denominator is a power of 2 times a power of 3. So it's easy to check those are subrings. And you get those by taking the ring generated over Z by a reciprocal 1/2 and 1/3. And more generally, you can do this with any set of prime numbers. If you take any set of prime numbers, call it S, you can take the subring that's generated by the inverse of those primes. So you take, and so another way to describe that subring is it's the set of rational numbers such that the denominator it is factors, is composed only of the primes in S. Yeah, in fact, you can prove that every subring, that every ring between Z and Q is one of these. It's a set that it's a ring that you obtain by joining the inverses of a set of primes. And this S, I mean, here I chose a finite set of primes. This was coming from the set 2, 3, but S, I mean, you can do this also when S is an infinite set, and you'll get a big subring of Q that way. Okay, so now you have all these subrings. You can ask Hilbert's 10th problem for each of those. So you have lots of things to discover. Okay, so yeah, so okay, here I'm just repeating that proposition from the previous slide that all the subrings have this form. And so now what you can imagine is, well, try this out for various sets. So if you take S to be empty, so if you don't invert anything, then you're just talking about the integers themselves, and Hilbert's 10th problem has a negative answer. If you invert all the primes, well, then you get all the rational numbers, and then we don't know yet whether Hilbert's 10th problem is solvable or not. Okay, but now we can. What about the S's that are in between? And you can ask, okay, so you can start making S bigger and bigger. How large can you make S and still prove a negative answer for Hilbert's 10th problem? And so Robinson had some work that implied that if you do it with a finite set S, so then you can still, you see her argument could be made to work to prove that the answer to Hilbert's 10th problem is still negative. So there's still no algorithm. So, but now we can start looking at the infinite set S, and you can measure how well you're doing. Yeah, you can measure. Okay, sorry, you can measure how well you're doing by looking at how many primes. I mean, you can measure how large your set S in the sense of density. For example, if you choose S to be all the primes, I mean, all the primes except 2 are 1 mod 4 or 3 mod 4, and if you choose S to be the set of primes that are 1 mod 4. That's in the sense of density, that's 50% of the primes. So if you can prove Hilbert's 10th problem is undecidable over the ring where you would invert all the primes that are 1 mod 4, then you get 50% credit. And so, well, you can ask, okay, how much credit can I get? And so, well, I was able to get 100% credit back a while ago. But I mean, 100% is not as good as it sounds when you talk about density, because you can have a set of primes of density 1. That doesn't mean it's the set of all primes. It just means that the complement is sparse enough that asymptotically its density is 0 among the primes. But okay, so anyway, so I was able to get this ring that sort of is almost the rational numbers, and over that ring that's almost the rational numbers, I could get a negative answer for Hilbert's 10th problem. But yeah, it's still not quite. I mean, nobody really cares about these rings, I think. So it's not the result I would have liked to have proved. I really would rather replace this by Q. But anyway, so the proof of this uses, I'm not going to describe the proof, but it uses properties of integral points on elliptic curves. Yeah. All right, so I've come to the end of my talk. So let me just summarize with this slide. So this shows, so I mean, there are lots of other rings besides the rings and fields that I didn't talk about, and you can ask about Hilbert's 10th problem for all of those. I mean, some of these questions are kind of stupid. For example, if I ask, can you find an algorithm that'll take a polynomial and decide whether it has a solution in complex numbers? Well, yes, you can do that, because pretty much every equation has a solution in complex numbers, unless it's a stupid equation like 5 = 0 or something like that. So, and also it turns out you can solve the harder problem for the complex numbers about the truth of whether you can decide the truth value of any first order sentence over the complex numbers. Now that's sort of the content. That's essentially equivalent to what elimination theory. And when you're solving systems of polynomial equations, there's a way to eliminate variables, which is a generalization of Gaussian elimination to nonlinear polynomials. And so that, yeah. And for the real numbers, it turns out that, again, there's a more complicated algorithm that answers the question. So this means that any problem of Euclidean geometry, you have this triangle and this circle, and the circle's inscribed in the triangle, and the in-center and all this stuff. Any statement like that, you can decide whether it's a correct theorem or not using this algorithm that was discovered by Tarski, because all those things can be expressed in terms of as a first order. Each theorem of Euclidean geometry like that is a certain sentence in the first order theory of the real numbers. And so, yeah, there's some kind of elimination theory that you can do there. Okay, and maybe this is the stupidest line of all. I mean, if you're dealing with a finite field, yeah, there's an algorithm to decide whether a polynomial equation over a finite field has a solution. You just try all the values and see if they work. And saying, yeah, okay. But there are all kinds of other fields. There are p-adic fields, like the field of p-adic numbers, QP, and then there's some analogs which is not known. And yeah, and this, okay, way down here, this is Matiyasevich's result. And over here, this is Julia Robinson's result. That for Q, we don't know about Hilbert's tenth problem over Q, but the harder problem was proved undecidable by Julia Robinson. And so, yeah, okay, anyway, there are all kinds of things here. And I've sort of ordered these in, okay, I mean, I've said increasing arithmetic complexity. I mean, there's no actual definition of arithmetic complexity, so this doesn't really mean anything, but, well, maybe you can sort of say that, for example, fields are more complex if they have a bigger absolute Galois group. Like the real numbers, the algebraic closure is only an extension with the Galois group of Z mod 2Z, so it's not very complicated. So, whereas for Q, the Galois group of Q bar over Q is really complicated, and so on. And okay, anyway, so okay, so yeah, so I think I'll end here. So thank you all for your attention, and I'd be happy to take any questions. Yeah, so thank you.
Thank you, Bjorn. I'll just clap for everybody. Thank you for a beautiful talk. Are there any questions? If there are not any questions, I had one. Like, do you have?
I saw somebody with a raised hand.
Oh, raised hand. Sorry, I didn't see.
Yeah. I have a quick question, but I could also ask after you.
Oh, go ahead.
All right. So, I mean, this is about actually like this explicit polynomial that you showed, like in this prime producing polynomial, I guess.
Oh, okay. You want to go back to that one? Yeah.
Not necessarily. I mean, I guess the question is that, like, and I guess for any listable set, you could produce like this. I mean, there's this universal polynomial, right? Which
right. So you could find a similar polynomial that output only the Fibonacci numbers, for example, if you want to.
Right. And is there any like degree? Like, is there a lower bound on the degree for those? I mean,
well, I mean, in fact, you can solve all such problems with. You only, in fact, you can do this with polynomials. The polynomials that you need to do this for different listable sets, you can choose them so they all have the same degree and all the same number of variables, because they'll all be specializations of one. Because there'll be all specializations of a single polynomial,
right?
That essentially simulates the universal Turing machine. So, and you just change if you want. So, if you want listable subset number 17, then you just plug in 17 for one of the variables, and then that gives you the corresponding whatever,
right?
Type 17 producing polynomial.
Right.
And so they're all, so I mean, the coefficients will get bigger, but the degree and then the number of variables will be just all the same. So
I see. But so it could be any number of, so it could be a degree 2, for example, that polynomial. I guess not. Right?
Oh no, actually for degree 2, there's a theorem that for degree, actually this is another interesting question. It turns out that for degree 2, for polynomials, multivariable polynomials of total degree 2, there actually is an algorithm to decide whether there's a solution. I mean, this is non-trivial. It depends on deep results of Siegel from the mid 20th century. And it turns out, on the other hand, if you go up to degree 4, then you can prove that solving polynomial equations of degree 4 in a large number of variables, that's undecidable already for degree 4, because there's actually an elementary trick you can do to simulate any polynomial equation by a polynomial equation of degree 4. Because maybe I'll tell you this later, but you can sort of build up a polynomial. You can turn a polynomial into a system of polynomial equations where each polynomial equation is like z equals x times y, w is z plus v, and then you can turn that system into one polynomial by doing the sum of squares trick. And so and so that gives you a polynomial degree of most 4 that's solvable if and only if your original polynomial is solvable. See, so yeah, so degree 4 is already unsolvable. Degree up to 2 is solvable, and nobody knows what's happening with degree 3.
Okay, thanks. Great.
I have a question. Can I ask?
Yeah.
So you have said this it goes harder to solve to know with the Galois group of the field. So
Oh,
is this
yeah,
the only thing we know, or other is there any other relation with the Galois group of the field? And
I don't know if there's any direct theorem that says, of the type that says, if the Galois group is like this, then Hilbert's 10th problem is unsolvable or is solvable. The proofs of these results, all these yeses and nos, each one sort of requires its own kind of argument. I mean, all these no's are eventually reduced, are eventually proved to be no by showing that the problem is at least as hard as the halting problem. They're all done by, I think, pretty much almost everything that's ever been proved undecidable. That maybe it's not quite true, but almost all the like natural problems that have been proved to be unsolvable have been proved unsolvable by proving that you can embed the halting problem in them somehow with some clever reduction. But yeah, so I don't know. Yeah, so I don't. Anyway, so going back to your question, yeah, I don't know if there's a theorem that says like if the Galois group is this, then the answer is going to be no, and if the Galois group is this, then it's going to be yes. Or I mean, there are other ways to measure arithmetic complexity too. You can measure. I mean, you could take the Brouwer group of the field, which measures like the quaternion algebras and central simple algebras over the field and how many of those there are. Or you could look at, I mean, there's something called cohomological dimension, which is, I guess, well, that's, I guess, related to the Galois group again. But yeah, there are various measures about how complicated a field is. But yeah, but there don't seem to be any general pattern. It just seems roughly more complicated the things are, so the greater expressibility you have when you're using the more expressive power you have when you're writing down polynomial equations. And Z somehow has more expressive power than Q, because in Z you can also talk about like divisibility, which you can express that using equations, which you can't do it directly using Q. So somehow rings tend to be even more complicated than their fraction fields. But yeah, but these are just heuristics. There's no theorem.
Thank you. Yeah, I see. Thank you.
Bjorn, there's a question on the chat which says,
oh, sorry, I haven't been looking at the chat.
well,
Okay.
I can sort of tell you. I mean, like, I think it boils down to, if you make some restrictions on the degrees and the coefficients, like, can you find like interesting classes of Diophantine equations for which Hilbert 10 is solvable?
Yeah, so there are some. So I guess I mentioned that if you restrict to degree 2, total degree 2, then that's solvable. Of course, degree 1 is also solvable. I mean, linear equations you can figure out. And as for fixing the number of variables, I mean, there's not very much known. I mean, even if, well, I guess if you have a polynomial in one variable, and you want to know whether it has an integer solution, I guess you can figure that out. I guess you use whatever rational root test or whatever you call it. I don't know what you call it in Turkish, but anyway. So yeah, but already when you get to 2 variable polynomials, then you're talking about deciding whether a polynomial equation 2 variables, you want to know, then you're talking about integer points on a curve. And it's not, already in that case, it's not known in general whether there's an algorithm to decide whether an algebraic curve has an integer point on it. And that's a big open problem that people have been studying for a long time. So for 2 variable polynomials, it's not already unknown whether it's solvable or not. But once you get up to I think it's 11 variables, then it's known that it's unsolvable. But there are, yeah, but like all the, yeah. There's a lot of space in between. So we don't know where the boundary is. I mean, my guess would be that for two variable problems, that for two variable polynomials, that there actually is an algorithm. Because there are a lot of conjectures in number theory, you know, related to ABC conjecture and Falting's theorem and something, things like that, that sort of suggest that probably there is an algorithm, although nobody's been able to prove it yet. There should be a method to decide whether a two variable polynomial has a solution, but I don't know where the boundary, there's going to be a boundary where things start becoming undecidable, and I don't know where that is between 2 and 11.
Any other questions for Bjorn?
I have a question.
Yeah.
I am wondering the details of the proof of the DPRM theorem. I mean,
Yeah.
I think you are encoding the transitions of a Turing machine via polynomial equations, right?
Yes, that's right.
How do you do that?
It's kind of a long story, but I mean, one of the key idea, yeah. I mean, Matiyasevich proofs actually used Fibonacci numbers. He actually proved surprisingly, he proved a new theorem about Fibonacci numbers that would let him decide, like, if he had like Fibonacci number Fn and Fm, and he wanted to know that n is related in some way to m, he found some way to do that with some polynomial equations. And I guess one of the key steps was to show that the property that that the equation a equals b to the c, where a, b, and c are integers. The equation a equals b to the c, Matiyasevich figured out a way to use Fibonacci numbers to show that a equals b to the c is equivalent to a polynomial equation in a, b, and c. And so in that way, he could simulate exponentiation using a polynomial equation. I mean, it sounds impossible, but yeah, that's what it turns out. I mean, actually, Julie Robinson played a large role in that too. She showed that if you could find any equation such that the solutions grew at the integer solutions had a certain rate of growth, the solution grew sufficiently fast, then she proved that you could have this polynomial equivalent to exponentiation. And then Matijesevich's contribution was to find that equation where the solutions grow quickly, and that was what used Fibonacci numbers, using the fact that Fibonacci's numbers grow at a certain rate and so on. And yeah, and then once you have exponentiation, then you can do all kinds of things. But it uses all kinds of other little number theory lemmas. There's a theorem of Kummer that tells you if you have a binomial coefficient, what is the power of p that divides the binomial coefficient? If you do high school math contests, maybe you know this. So there's something where you write your m. If you're looking at m plus n, choose m. You write m and n in base p, and you count how many carries they have, and you add them in base p, and so on. But anyway, so there are all kinds of little number theory tricks like that are used. If you want to read about it, I think the best place to read it is, I mean, this proof got simplified a little bit over the years. It's still quite long, but there's a book by Matiyasevich called Hilbert's 10th Problem. I think that's the name of the book, and he gives the full proof there. That's relatively efficient. Yeah, but you build up like a register machine, and you have your integer variables are encoding the state of your Turing machine, and you have to write equations that sort of tell you like what does it mean for this equation, like for this state to be the next state of the calculation. But yeah, anyway.
Thank you.
All right, Bjorn, I know you need to go soon, so we'll thank you again for a wonderful talk. I'll just clap for everybody. Thank you very much.
Yeah, it was okay. It was fun talking to all of you. So yeah, thank you all for coming.
Bjorn.
See you
Bye.
later.